Hello everyone. I'm just going to rewind galaxy evolution back 13 billion years to the reionization epoch. And I'm going to tell you a bit about our most recent results over the last year, essentially that we obtained with the XDF team, led here by Garth Illingworth in Santa Cruz, Richard Bowens in Leiden, and also I want to point out in particular Ivo Labbé, who is really important for our Spitzer IRAC photometry. And so I'm assuming over the last couple of years you have all heard that we have made really great progress in exploring the reionization epoch. We are now able really, thanks to the V3 IR camera and through surveys like our UDF09 survey, like the Candle survey here led at UCSC, we are really able to push into the epoch of reionization. We have large samples of galaxies, redshift 7, 8, and so we can address some of these questions. When and how did the first galaxies form? How fast did they grow and build up? And so today, in particular in the second part of my talk, I want to combine our HST imaging with very deep rest frame optical imaging from IRAC, and so we can get a constraint on the star formation rates from HST and on the masses from IRAC. And so also over the last couple of years, we really established this cosmic star formation rate density plot. From the peak at redshift around 2, it really monotonically decreased to redshift 8 or so. And already last year I was telling you that we had good evidence that at redshift 10 the evolution was accelerated. Today I'm going to be showing you new measurements at redshift 9 and also better constraints at redshift 10 now. And this was made possible in particular by new data over the Hubble ultradeep field with the UDF12 program led by Richard Ellis. They got 128 more orbits of V3 IR imaging. And in particular, the important thing is that they added F140 filter imaging, which now really allows us to separate redshift 9 from redshift 10 galaxies. And so over the next couple of slides, I'm going to be showing you a redshift 9 search that we did over the Hubble ultradeep field only. It's a very small, of course, 4.7 square arc minutes. And then a wider area search for redshift 10 galaxies over all the V3 IR data in the Chandra Deep Field south. And so we have data ranging from essentially 30th magnitude here over the Hubble ultradeep field in H-band to essentially 27.5 in candles wide. And just quickly to advertise our XDF image, essentially we combined all the HST imaging that was taken over the last couple of years. Essentially it's a 2 megasecond exposure in ACS and V3 IR that was taken over the Hubble ultradeep field. We combined it all, reduced it to this nice color image, but of course we also have the separate bands. It's all available on our webpage here, xdf.ucolic.org, or also on MAST for you to use. So that was just a quick advertisement. And now we're using this image, essentially, to search for redshift 9 Lyman break galaxies. And of course, we make use of the fact that by redshift 9, we are in the heart of cosmic reionization. And so there's a lot of neutral gas around, of course. And so everything shortward of Lyman alpha, essentially, is completely absorbed. And so you can make use of this fact using the broadband photometry, essentially combine different filters to make a color diagram where you can select redshift about 9 galaxies in this box up there, which separates off from the lower redshift galaxy population. And in addition to this color selection, we also use non-detections, of course, in the optical. We use a pseudo chi-square measurement, which combines all the flux information that you have in the optical bands, and that really helps us to push down the contamination rate by a factor of 3 or 4 or so. And so applying these selection criteria, we come up with a sample of 7 candidate redshift around 9 galaxies, between 28 to 29.9 magnitude, photometric redshift on average of 8.7. And so these are the sources here. You see stamps, different filters. You can see the bright end there, of course, very nicely detected. They start to disappear between Y and J. And that's, of course, how we selected these sources. And as we go to fainter and fainter luminosities in the H-band, you can see this faintest source here is still well detected both in 2 filters, but then shortward of essentially the 140 imaging, the data unfortunately is not deep enough to establish a very strong break in the source. So the best photometric redshift for this source, unfortunately, is essentially 2.2, depending on the template set that you're using or the CD fitting code. And you can see here the redshift likelihood distribution function has a strong peak at low redshift. So that's for this source here, but you can also see similar low redshift peaks in most of the other sources. And the question then, of course, is, well, what is the contamination rate, and what is which sources are at redshift 9? And so essentially we do a Monte Carlo estimate of the contamination rate. Essentially we assume the low redshift solution is the right one. We apply photometric scatter and then see what fraction of the time these sources are selected as a redshift 9 Lyman break candidate. And so it turns out, out of these 7 sources, per realization you expect 1 contaminant. And so essentially a contamination rate of about less than 15%. And so I'm essentially removing this one source here for the rest of the analysis then. And so we can compare with the results from the UDF-12 team, from Richard Ellis, and actually they use a photometric redshift selected sample. We use Lyman break selections, the result, the comparison is actually really great. Essentially, they have 2 sources in their sample that we don't have. This one here is, I think, a diffraction spike. This one is just outside of the selection box, of our Lyman break selection box. Then we have a few additional sources, but we have a broader selection window. So I think the overall agreement is really great. So there's this one source here that is marked 11.9. That source is somewhat mysterious. This was our best redshift 10 candidate in our UDF-09 data. So before the last year's data came in from Richard Ellis. So I was telling you about this last year, I guess. And so the thing is, this source is not at all detected in the new 140 filter imaging. It's clearly there in the H-band, and there's a 2.2 essentially magnitude break between 140 and 160. And so the thing is that this source, 140 and 160, they essentially overlap completely. And if we're seeing continuum imaging here, this source would have to have a break at 1.6 micron or so. So this source cannot be at redshift 10. Rather, it would have to be at redshift about 12. Now, if it was at redshift 12, intrinsically this source would be essentially a factor 20 times brighter than what we would expect it to be for a redshift 12 source in the UDF at this number density. And so that's relatively unlikely. But another solution that we might have is that this is emission line flux that we're seeing here at around 1.6 micron. And indeed, there's a very, very tentative line detection from GRISM data. There's another very tentative line detection from MOSFIRE data. But at this point, we really don't know if that's true, if that's a real source, if that's a real emission line. Certainly, there are sources with these extreme emission lines, 0.3, but they're also extremely rare. So at this point, I'm going to treat this source just as an upper limit at redshift of 12. So we have one additional redshift 10 candidate, though, which is this source here that's now clearly detected in the H-band, clearly detected in 140. Again, it's very faint, 29.8. Has a best fit photometric redshift of 9.8. Again, with a lower redshift peak that we cannot rule out a contaminant. However, even if this source was not at redshift 10, we have a very interesting result. Again, if we extrapolate the luminosity function trends from 4 to 8, extrapolate this out to redshift 10, in the full data set, we essentially would have expected to see 9 sources by now, 9 redshift 10 candidates, if the trends just continued. And we find 1 candidate here at the very faint end. And so that's clear. If you expect 9, you find 1. Even if you include cosmic variance, there's clear accelerated evolution going on. And so we see this in our constraints of the luminosity function. I'm not going into that. But essentially, we have here the luminosity density as a function of redshift. Now, this new redshift 9 point here from these essentially 7 sources. And then here our new measurements at redshift 10. And so you can see there's clear downward trend down to our current detection limit. I don't think that's very surprising. A lot of theoretical models actually predict a relatively steep evolution between redshift 7, 8 out to redshift 10, and I think that's mostly driven by the underlying evolution of the dark matter Hilo mass function rather than any physical changes in the star formation. And then we are not the only ones, of course. Not the UDF is not the only field where you can look for these high redshift sources. In particular, Flash found a very nice candidate here at redshift 10.7. So they make use of the lensing magnification of foreground clusters. This source is triply imaged at photometric redshift at a site of 10.7. Here's another example at 9.6. And so with HST, we're starting to build up the star formation rate density diagram at redshift beyond 8. And so this is plotted here, again, down to our current detection limits. I think all the authors agree at redshift 9 there's a clear drop from 8 to 9 by factor 4 to 5. And then beyond that, unfortunately, all these data points only contain one single source, so the uncertainties are still quite significant. But when combining all these measurements, as clear downward trend, accelerated evolution beyond redshift 8. As I said, uncertainties are still large. We're going to have new HST data from the Frontier Field program over the next 1 or 2 years. So this is going to be great. It's going to really constrain the redshift 10 point again. But then beyond that, of course, JWST in the not so near future is going to pin down all this evolution. Okay, so now let's include Spitzer IRAC in the second part of my talk here. As I said, we really want to have a rest frame optical measurement if we want to get information on the stellar masses, otherwise they're totally uncertain. And so that's why we set out to do our IUDF program. We got very deep imaging, 26 hours essentially in 3.6 and 4.5 over the Hubble ultradeep field, and also very deep imaging over our UDF-09 parallels. And so one problem here, of course, with Spitzer IRAC is that the PSF is essentially 10 times broader than the HST PSF. And so you have to do quite sophisticated neighbor subtraction. And so essentially we are modeling all these sources based on the HST imaging. We have kernels that convolve these to the IRAC image, subtract these neighbors, and then you can perform photometry on the clean source itself. And so doing this, essentially we managed with the IUDF-10 program for first robust detection of 9 redshift 8 candidates at more than 5 sigma. And here's an example of one. Here, this is the GOODS 23-hour image. Now with IUDF 120-hour, you see there's a clear detection, 9 sigma. So 30% of the sources have rest frame optical detections at redshift 8. And then for the others, we can, of course, do stacking. And you see clear detections in both filters. And so you can get the constraints on the spectral energy distribution at redshift 8. And so we find that a typical galaxy at these redshifts has essentially about 10 to the 9 solar masses already. It's an L-star galaxy. We can then, of course, also constrain stellar mass functions, that was done with Valentino Gonzalez. But one big problem that we have here, one caveat, is strong rest frame optical emission in these galaxies. And you can clearly see this if you stack the photometry from galaxies where you have H alpha outside or inside the 3.6 micron image, Spitzer IRAC image. And so you see that there's a clear excess of about 0.3 magnitudes, so indicative of like 300 angstrom or so rest frame H alpha. And so unfortunately these emission lines are evolving to getting stronger at higher redshifts. And so these are going to be extremely important, in particular redshift 6 and 7, where you have emission lines in both bands. And so then Stark did an empirical correction essentially for this. Redshift 6, 7, you get a factor 2 to 3 lower mass densities if you include this. But after the correction, essentially the stellar mass densities and the star formation rate densities are actually in quite good agreement. Okay, so I guess I was running out of time. So the only one point that I want to make is that, of course, Spitzer-HiPACC is also extremely important if you want to constrain dust extinction at high redshift. In particular, well, dust extinguishes the UV, and with HST we only probe the UV. And the important part here is that if you bin the SEDs of galaxies from rest frame UV, it seems like these SEDs are all self-similar. They all look exactly the same. Well, if you have a rest frame optical view and you bin these SEDs in rest frame optical, you see that at high masses, the galaxies are much redder, much more dust extinguished, and so on. And so rest frame optical is really, of course, going to be a very important ingredient for a self-consistent picture of mass and star formation rate buildup at these high redshifts. And it turns out that there's a large data set out there. The S-candles data, essentially 50-hour exposures over all the candles fields. We have a huge sample of sources, 10,000 redshift above 4 galaxies. And so this is really going to be a great resource for mass functions, for duty cycles of star formation that we haven't really been able to address with the small samples that we had so far. Okay, and so the future is bright, and I'm just going to leave up my summary here. Thanks.
Pascal, time for questions. Who wants to go first? Students. We haven't heard very much from students. I'm not a student asking the first question. You're not a student anymore. You look like one, but you're not one. All right, Charlie first.
Okay. You commented just in passing that the star formation rates and star masses are consistent at high redshift.
Yeah.
Is there any epoch at which they're not consistent anymore, or is it all the data from redshift 0 to whatever?
No, at redshift 2 actually, 2 to 3, the stellar mass densities are lower than the star formation rate. I mean, the star formation rate, you infer a higher stellar mass density than what we actually see. And yes, not a lot, a factor of 4 or so. I mean, it's within, so it depends, I guess, Naveen Reddy sort of pointed out that it might just be a dust problem, that if you...
It's good at high redshift and it's good at...
I know, yes. Yeah, so who knows, but I mean, you know, if it depends, right? If you have stochastic star formations, I mean, we might not be estimating our star formation rates right. And so that the masses might be off as well, and you know, it might just be a coincidence. I don't know, but at this point we don't have evidence for a big problem. So, yeah.
All right, David.
Are all your high redshift objects clearly spatially resolved? Are they non-stellar? Can you say that or not?
For the bright ones, yes. So for the bright ones, we obviously check, right? For the bright ones, it's clear that they are resolved. For the faint ones, the signal to noise is just, it's low. So I cannot rule out a point-like source.
So there are no stellar type of objects that could satisfy your color constraints?
No, well, you know, with photometric scatter,
Rare, red stars, some sort of thing?
No, yeah, LT dwarfs are usually a problem at redshift 7 or so because of absorption. Here you see the stellar locus in green here, and of course with photometric scatter you could have something, you know, scatter up there. Yeah, but again, well, who knows? Yeah.
Objects, so obviously it doesn't help.
Ha! Yeah, no, that's true. Yes.
All right, question?
So you mentioned the duty cycle. I was wondering how well you can actually constrain that from the future surveys by looking at SEDs. If it's really dominated by the stochastic bursts in high redshift galaxies,
Yeah, I mean,
it tend to be bluer and puffy. And so can you really constrain it in the future with hopefully JWST data?
well, okay, so with JWST you get emission lines, right? You get the rest frame H alpha or something like this, and so from that, I think, yeah, you can certainly do something much better. For now, well, I'm hoping to compare with simulations. Essentially, we have to make models, but the thing is that for now, mostly what we were doing is stacking, you know, SEDs, and so. But if you have large samples of individually detected sources, right, you can start to measure like the RMS in the star formation rate mass relation, and so you have a handle on this, yeah. But what you really want to do is compare the UV star formation rates with the H-alpha star formation rates, and then the masses. And so, but that's going to be further along.
Okay, we'll stop there.
Thank you.
Pascal.